Hello and welcome. In this video, we're going to look at how to calculate our series capacitance, and then we're going to measure that, and we're going to compare our measurement to what we calculated our capacitance to be at. Okay, so the first thing we need to do is evaluate this. This circuit looks to be a fully series circuit with 3 series capacitors in them. We know series capacitors act a lot like parallel resistors, right? They're a little bit backwards. So we're going to place this into our equation for series capacitance, 1 over, and we know that each of those are in picofarads, and so I can just say 1,000. And we'll add that to the 1 over of our next one, 2,200, plus 1 over 1,500. Right, those are all in picofarads. It means that this answer is in picofarads, and that is what we expect our total capacitance to be in this circuit. So we can write that down. We'll say that our CT is equal to 471. We can round that rest off, and that is in picofarads. Okay, so we're going to verify using this number that our measurements are going to match, right? And so to do that, we have to measure them, and we do that with our LabVIEW instrument. So on the sidebar on the right here, you drop down that, and you can get the second one out. That's the impedance meter, or you can go up to your Simulate tab, Instruments, down to LabVIEW Instruments, and then click your impedance meter from there. Note that this impedance meter sends a frequency through our capacitors, right? So to measure capacitance in picofarads, we actually have to measure capacitive reactance and then convert that into picofarads. So we have to remove our voltage source. That's the first thing we do. So we'll right click and delete that voltage line, and we'll attach our line here, our positive side, to where that voltage was. And then the negative side goes to ground. We don't have to remove the ground line from that because we just need to remove the potential from it. And then we can induce a frequency through it. So when we double click on this, we're given a new window here. And this is going to induce a frequency within this range. And so if we wanted to do a sweep of frequencies, we can range this sweep here. We're going to leave it at 60 for both of those two. So we have a consistent frequency when we hit play on this. We don't have any resistors, so we expect that to be really low. And then we should see the difference between our X and our Z here. So let's hit play. And so our X value is actually reading like an inductance. And so it shows it negative because our capacitors are on the negative side of our imaginary numbers, where inductors are on the positive side of our imaginary numbers. And so in this case, we're going to take this number here, and we're going to use that as our total capacitive reactance. So we have an XC of 5.63 million. XC equals 5.63 mega ohms. All right, that's really big, but that's just because we have a really small frequency, right? 60 hertz going through these capacitors. That means these capacitors can be a little bit larger. And so we can use that to determine if our total capacitance is matching. And there's a question mark here that gives us those equations that we need. So we click on that, we see it's 1 over 2 pi fc. And so we're going to use that 1 over 2 pi fc is equal to our xc value, and we're going to calculate out c. Let's get that out. So we'll get rid of those and say that we have xc is also equal to 1 over 2 pi. That's our frequency, right? That's our circle, our f and our c. And this is actually going to be our CT in this circuit. It's going to be our total capacitance, right? So we know most of this. We know our xc is 5.63 mega ohms. It's massive. And that's equal to 1 over 2 pi. That's our circle. Frequency we said was going to be 60. And we don't know what our CT is. We're going to calculate that out. We're going to solve for CT. Okay. So the first thing that I would do with this one is get rid of that 1 over, because that's not very nice to work with. And so to get rid of this top here, we can actually take the inverse of both sides, right? So if we multiply this whole thing by -1 and this whole thing by -1, then that'll get rid of this and that -1 from this side, and we'll just have to evaluate it on the other side, right? And so then we can rewrite this and move on with our reduction here, because now we have 5.63 mega ohms to the -1. That's the same thing as 1 over 5.63 mega ohms. And we'll set that equal to 2 pi times 60 times CT. And so all we have to do now is remove that 60 times CT to the other side also, or 2 pi. So 2 pi times 60 goes to both sides. So divide 2 pi times 60. And so we'll evaluate this side, and that'll be equal to our CT value. So CT is equal to, We can solve that out. Send this out, and we'll say that we have a really large number up here. So we're going to put that in its own little parentheses, and we'll say that that is 5.63 times 10 to the positive 6 for that millions of ohms. And we'll close that off and give it a negative inverse. So we'll say to the negative 1, and that deals with that other side there. And so after that, we can put another parenthesis out there and then divide the whole thing by our bottom, which is 2 pi. 2 pi times 60. Right, and that gives us this number here. So we're going to use that as our CT. Let's pull that number in. So CT is equal to 4.71 times 10 to the negative 10th. Negative 10 doesn't work for us, so we need to move it back to the negative 12 because that's what our original CT was calculated at, right? Pico. Pico is negative 12. So we'll say that our final CT that we measured here is 10, 11, 12 back. So we'll move it 2 back. 471 times 10 to the negative 12, which we know is picofarads. And so they match. That's what our goal was, to match these two together and verify that our measurement of these capacitances match what we expect them to be. All right, let me know if you have any questions.